This is the pre-lab for the experiment Relative Reactivities of Activated Aromatic Compounds. In this video, I will cover the pre-lab assignment, safety information, the goals of the experiment and the methods you'll use to achieve them, some background information, details on conducting the experimental procedures, important information about cleaning up, and some information about analyzing the class data. Prior to lab, you need to read all of the assigned sections in Techniques in Organic Chemistry and in your Organic Chemistry lecture textbook. You also need to prepare your notebook using the preparative format. Make sure that you follow the special instructions in the lab manual and only write up what's needed for the bromination of your assigned compound. Also, since you don't know whether your compound will produce a mono, di, or tribromide, you need to calculate the theoretical yields for all three in advance. That way, when you determine which product is formed, you can quickly calculate the yield of the reaction. Some of the reagents you will use in this experiment require special care and handling. Bromine is highly toxic and highly corrosive. Its vapors can damage the eyes and the respiratory tract. So, you need to wear gloves, and you'll need to dispense it in the fume hood. You'll also need to take care to avoid skin contact and breathing the vapors. Acetic acid is corrosive and highly irritating to the eyes and the respiratory tract. It should be handled in a manner similar to the bromine. Aniline, one of the starting compounds, and aniline-derived compounds, the products you make from it, are generally acute toxins. So, if you are assigned aniline as your starting material, avoid contact with your skin and breathing the vapors from aniline and your brominated aniline products. If you do get some of the aniline or aniline products on your skin, you'll need to rinse the affected area under running water for 10 minutes. Your goals for this experiment are to synthesize the brominated derivative of your assigned compound, determine what brominated derivative you made, and then using data from the entire class, determine the relative reactivities of the three compounds in the experiment: aniline, anisole, and acetanilide. To do this, you will carry out a simple bromination of your compound in glacial acetic acid solvent. You will isolate the crude product by precipitating it from water. You will purify the product by recrystallizing it from methanol, and then you'll characterize it by melting point in thin layer chromatography analysis. Some background. Elemental bromine reacts rapidly with isolated alkenes, something that's often done as a simple qualitative test for their presence, but it fails to react with benzene under similar conditions. Benzene can be made to react with bromine with the addition of a Lewis acid catalyst, but the reaction occurs as a substitution rather than the addition reaction we observe with simple alkenes. This reaction isn't unique to benzene alone. It's also observed in derivatives like toluene, which also doesn't react with elemental bromine alone, but does react when a Lewis acid catalyst is present. In this case, it gives a mixture of ortho and para bromides. The reaction between an arene and bromine is an electrophilic aromatic substitution. It can be described as a Lewis acid-Lewis base reaction, where the Lewis base, or nucleophile, electron pair donor, is the arene, and the Lewis acid, or electrophile, electron pair acceptor, is the bromine. Arenes, like benzene and toluene, are quite stable, and thus only weakly nucleophilic. Bromine, in the absence of a Lewis acid catalyst, is only weakly electrophilic. At a more fundamental level, we can understand what's necessary for a reaction to occur by considering the interaction between molecular orbitals of benzene and bromine. Benzene's the nucleophile, and thus the electron pair donor. The electrons that it donates most readily are those that lie in its highest energy occupied molecular orbital, the so-called HOMO. Bromine is the electrophile. It accepts those electrons, and that occurs most easily into bromine's lowest energy unoccupied molecular orbital, or LUMO. For the reaction to occur, the energy gap between these orbitals needs to be reasonably small. In this case, the energy gap is large. Benzene is quite stable, and the energy of its HOMO is relatively low. This translates into it being a weak nucleophile. In bromine, the energy of its LUMO is rather high, which translates it into being a weak electrophile. The result is an energy gap that isn't easily overcome under ordinary conditions, and no reaction occurs. So what happens when we add iron bromide that allows a reaction to happen? The answer is that it coordinates with the bromine, producing a complex, and in doing so it lowers the energy of the LUMO of bromine. This makes it into a strong electrophile because now its LUMO is low enough in energy that the electrons easily transfer from the HOMO of benzene and the reaction occurs. While benzene and toluene are weakly nucleophilic, some aromatic compounds, particularly those with atoms like oxygen and nitrogen directly attached to the ring, are more strongly nucleophilic. Phenol, shown here, is one such compound. And even in the absence of a Lewis acid catalyst, it is sufficiently reactive with bromine that it readily forms the tribromide derivative. In orbital terms, the presence of the oxygen atom raises the energy of the HOMO of phenol, such that it's in the range of the LUMO of bromine and the reaction occur. This higher energy HOMO means that compared to benzene, phenol is a strong nucleophile. The reason the oxygen atom raises the energy of the HOMO and increases the molecule's nucleophilicity can be rationalized in terms of the electron donating effect of the oxygen lone pairs. We can draw resonance structures such as these that indicate that some of that electron density is donated to the ring. In composite, we see that the ring takes on a partial negative charge at the positions ortho and para to the oxygen. The result is that these positions are nucleophilic and readily react with bromine, leading to the tribromide above. Now, one curious aspect of this resonance effect is that it is counterbalanced, to at least to a small extent, by the inductive effect of the electronegative oxygen atom. Since it is more electronegative than the carbon and hydrogen atoms in the ring, one would expect it to inductively draw some electron density out of the ring. It's clear, however, from this case, with the bromination reaction above, that the electron donating resonance effect far overwhelms any electron withdrawing inductive effect. Here are some tips for conducting the experiment. When you're running the reaction, be sure to add the bromine slowly, dropwise, with a Pasteur pipette. You should be able to observe evidence of the reaction in the quick disappearance of the red bromine color almost immediately after each drop is added to the reaction, at least at the beginning. After all the bromine's added, you may end up with anywhere from a deep red to a light yellow mixture, depending upon which compound you started with. One of the compounds reacts with nearly all the added bromine, resulting in a light-colored reaction mixture, because there's very little red bromine left over. But another of the compounds only reacts with one equivalent of bromine added, and this leaves over 2 equivalents of molecular bromine in the mixture, and thus a deep red color. Regardless of the color of the reaction mixture, the next step is to add water to precipitate out the crude product. This also needs to be done slowly, at least initially, by adding a few drops at a time from a Pasteur pipette. During the addition of water, the product will fall out of solution. In the case of aniline and acetanilide, the product precipitates out as a fine powder. Anisole, on the other hand, has a tendency to form an oil at this point. But with a lot of stirring and scraping of the oil against the sides of the flask, it will eventually turn to a solid. At this point, you have a mixture containing a considerable amount of solid product and a liquid that may range from a light yellow to a deep red color, depending on your starting material. The color's because there's still bromine present, and it needs to be dispensed with before you filter the product. You do this by adding concentrated sodium bisulfite to convert the remaining bromine to colorless water-soluble bromide ions. Bisulfite is a mild reducing agent, and it reduces bromine to bromide, while it in turn is oxidized to sulfate. It's actually quite simple. While you stir the mixture, you add drops of sodium bisulfite solution until you no longer see the color change. After that, you filter the product with a Buchner funnel, wash it with portions of water, let it sit for a few minutes with the vacuum running. What you end up with is a pasty crude solid that's still damp with a little water, but can be purified by recrystallization from methanol. Before you start the recrystallization, collect a very tiny sample to analyze by TLC alongside your recrystallized product. That way you can see by TLC what the recrystallization has done to your material. You'll want to conduct the recrystallization in a 125 milliliter Erlenmeyer flask. Depending upon your starting material, the amount of methanol you'll need to make the hot saturated solution for recrystallization will vary quite a bit. Typically, we observe that the aniline product takes about 75 milliliters, the anisole product about 25, and the acetanilide product only about 15. Another issue you should be aware of is that the products can melt before they dissolve in the methanol when you're making the solution on the hot plate. This results in an oily mass at the bottom of the flask. You simply treat that oily mass the same way you would a solid and keep adding solvent until it is dissolved and you have a homogeneous mixture. Cleaning up for this experiment is straightforward. The aqueous washes can be flushed down the drain. The methanolic filtrates from the recrystallization must be placed in the organic waste container, and the solids go in an appropriate waste container. Finally, a bit about data analysis. Since you need data from your classmates who started with different compounds than you did, and they in turn need your data, before you leave the lab, report your melting point and TLC data to your instructor. Your instructor will compile the data and distribute it to everyone in the class. And lastly, the most important part of the analysis is providing a clear rationale for the order of reactivity that's observed for the three compounds in the class data. It's essential that you provide appropriate, accurate illustrations, such as resonance structures, indications, dipoles, whatever, that support your rationale. Remember, a picture's worth 1,000 words, and that's particularly true in organic chemistry.